Yayındayız hocam. Başarılar diliyorum. Kolay gelsin.
Evet, teşekkürler. Hello, good morning, everyone. Today, we will continue our session and with our guest speaker, Professor Omer RANA from Cardiff University, United Kingdom. And he is joining our session from England in early time. It's 6 a.m. in the morning, 7 a.m. in the morning. Actually, Dr. Rana, Professor of Performance Engineering at Cardiff University with research. Interest is high performance distributed computing, data analysis, multi-agent systems. Also, he leads the complex systems research group. Actually, he was formerly the deputy director of the West E-Science Center and had the opportunity to interact with a number of computational scientists across Cardiff University and UK. Also, he has a collaboration with Dr. Jeffrey Farks, and also he has joining mainstream committee of the Cardiff University in data innovation and energy systems research institutes. Also, he has good contribution to specification and standardization activities via the open grid form. Maybe you heard about that. And we work in London-based Marshall Biotechnology Limited before joining the Cardiff University. Also, he has some research related to biotechnology. Also, he also contributed to public understanding of science, the Wellcome Trust Fund Science Line in collaboration with BBC in Channel 4. Also, his research and PhD, he has a PhD in neural computing and parallel architectures from Imperial College London University, and a Master of Science in Microelectronics, University of Southampton, and BS in Information System Engineering from Imperial College London University. He serves on the editorial boards and associate editor of IEEE Transaction on Parallel and Distributed Systems, formerly, then Transaction on Cloud Computing, IEEE, and IEEE Cloud Computing a magazine, and ACM Transaction on Internet Technology. He has actually many publication and research, and still he is active and contribute to this domain, high performance computing and cloud computing area. And he is very welcome to join our morning guest speaker session. And thank you very much, Dr. Rana, for joining us. And I will introduce you up to, I will give it to give microphone to you. On the title of actually we have is artificial intelligence, the new operating systems, and also I type on the chat session the abstract, and you can read the abstract. Again, thank you very much, Doctor, and I will give microphone to you, and thank you again.
Thank you, Professor Topku. So it's a great honor to be here. So assalamu alaikum, so good morning. So I hope we can generate more discussion. So you have my email here if people are interested in following up some of this discussion. So this is a different kind of talk than what you would normally get at a conference. This talk is really about initiating a discussion, a dialogue between our colleagues here in Cardiff and you guys in Turkey, and identifying potential research directions in this interesting area of how artificial intelligence and the emerging area of systems and machine learning work together. So, you know, you cannot start a talk without a Dilbert cartoon. So how long would it take to create AI that is as smart as humans? It shouldn't take me long to dumb down a computer to human levels. So I think AI is viewed by many people today as a core and important technology across a number of different sectors. So what this talk tries to do is to contextualize this work with three core questions. And here are the three questions which I think I wanted to start this dialogue with. So if artificial intelligence techniques are embedded in our systems and software environments, how should a developer respond to this? So what does that mean? So essentially the idea here is that increasingly computer systems vendors, whether they're NVIDIA or IBM or ARM, which is ARM was recently, for example, bought by NVIDIA, are increasingly trying to embed artificial intelligence techniques, whether it's machine learning or rule-based AI techniques within their systems. So if I'm a developer or I'm a programmer who makes use of these systems, to what extent should I reuse the technology that is already there within my system? So should I recreate, for example, should I redo what the system developer is already doing as part of their libraries, as software libraries? Should I reuse in the sense that can I just take what is already part of that system environment and try to extend it in some way? So should I extend, should I adapt, or should I just ignore what's in the system because, hey, I don't know what's going on anyway? Because most people in AI seem to focus very much on trying to enhance the capability of my software, but not to really tell me what is actually going on. So trying to explain what the AI does within the system is often remains a challenge. So that's the first question that I think I will try to address in this talk and a starting point for this dialogue. Right, so the second question is, should we differentiate between artificial intelligence as an enabler versus artificial intelligence as an application? So what does that mean? So essentially what that means is we are increasingly utilizing machine learning techniques with our computational science application. So there was an excellent talk by Jeffrey yesterday about how we can integrate AI with computational science. So if I have large-scale computational science problems, how I can integrate machine learning techniques, especially deep learning, within my application itself. So my question here is that should we really try to use AI as an enabler, as a way to do something or enhance something, rather than just as a type of application strategy or an application enhancement strategy? And to what extent is this possible? Right. So that's the second type of question that I would be considering. And finally, the last question, which I think is very important in this context, is to what extent should we trust the outcome of artificial intelligence-based systems? So essentially, this question is saying that how do I know what the AI is actually doing, right? So if I'm utilizing AI as part of my machine learning system within a computer system like NVIDIA or ARM, how do I know what the system developers have actually done to enhance the performance of the system? So often the key question currently is really about improving the response time or the latency or the throughput of my underlying system, but not telling me what the system is actually doing. So how do we decide how much to trust what is already there within the box, right? So these are the three questions that I think are very relevant. And this talk will try to address some of these and invite you to maybe work with us in exploring some of these questions. Okay, so to continue on with the first part, so if you look today at what is happening in high performance and cloud computing, so we can think of a picture like this. So essentially we have different devices that sit at the edge of the network. So we can have mobile devices, for example, that these are wearables to in-vehicle networks. So this is becoming a very significant growth area where we're trying to embed capability within our autonomous vehicles, for example, right up to high-end acceleration devices, which are primarily integrated within data centers and high-performance computing resources. So if I look at the profile of these devices, so devices that sit on this end, I really have data volumes of the order of megabytes to gigabytes and about 1 watt of power consumption. And if I look at the other end of the spectrum, my data rates are of the order of terabits per second to about 100 teraflops or more. And power is about the order of about 100 watts in terms of consumption of these devices. So what currently happens is that this data is pushed into a backbone network. And then often the data processing takes place across a cloud platform. And so essentially the data capture sits at the edge and analytics takes place in the cloud platform. However, increasingly with the availability of edge computing, we are pushing the cloud towards the edge of the network. So what we'd have normally done in a cloud environment is often now part of the devices that sit over here in the edge of the network. So essentially what that means is that whereas we often consider machine learning to run in the cloud, and we use libraries like TensorFlow and Keras, for example, to run in the cloud. But in fact, the cloud is all of these, right? The cloud is not just the data center. The cloud is also the edge. And increasingly, the cloud is also the network, right? So with increasing availability of software-defined networks, like with POX, which is a Python-based controller for network software-defined networks, and with OpenFlow and OpenDaylight and Ryu, we are increasingly opening up the network itself, right? So what does that mean for AI, right? So what that means for AI is that our learnings, the potential set of parameters that we have within our AI learning models are now no longer restricted to the data center. So we're not just interested in, improving throughput of tasks or improving the response time per task when we run a workload on a cloud. But in fact, it's also how we partition our application between the cloud, the data, the network, and the edge. So partitioning becomes a very, very important part of this new surface of parameters that we now have available with increasing use of edge computing. So software-defined networking, which sits in the middle, enables a telco operator, the telecom operator, to merge with a data center, right? So now the data center operator, which is like Amazon Web Services or Microsoft Azure, are no longer separated from the telco operator. The telco and the data centers have to work together in terms of some combined functionality. And that again opens up the potential range of parameters we have that we could feed into our machine learning models. Okay, so you can think of it like this, that if I have a workflow, or in IETF, the Internet Engineering Task Force calls this a service function chain. There's actually a working group at IETF looking at service function chains, where I have a set of services or functions that can be combined together, where some of the functions may be running at the edge, some running within a network using something called network slices through the use of SDN and network function virtualization, and then the others running on a data center. So combining these three things together is really a very important part of this. Okay, so this is some work we've done recently that tries to take this model a little bit further. So what we have here is this idea that suppose I have a bunch of subscribers that sit at the edge of the network. So this could be a video feed or a file feed that you want to push into the network. And then on the other side, we have the destination nodes. The destination nodes could be a data center or it could be a mobile device. Okay, so what we really want to do here is essentially to we want to insert, sorry, just let me remove this. So what we want to do is to essentially remove this idea that when a flow goes to the network, we have these intermediate routers or switches that are part of my path. These paths are shown here in these dashed lines. So the video starts from the video server. It goes to a firewall. It goes to a network switch. It goes to a video enhancer, to a video decoder, which could run, for example, within a function running on the network to a destination node. So what we want to do is to insert network functions from source to destination. And we want to do reservation of slices on the network in order to host our network functions. So what we're doing here is really to create a multicast tree that enables a dynamic data path to be configured from a video source to multiple destinations, right? So the objective of this delay-aware network slicing is to maximize the number of multicast requests that I can service through this network by combining these network functions as part of my end-to-end chain, right? So now the key question that work is trying to address is that performance is not just about what you do at the data center, but performance is also what you do along the whole path from the data source to the end node to the destination. So we have a paper that explains this in a little bit more detail. Let me just move this, sorry. So these are essentially cloudlets that can run on these, so very small functions that run on these switches. And this paper, you can read a little bit more. It identifies how these optimization problem of trying to find this path can be established from data source to the destination node. And this is our infrastructure that we use to deploy this. This is a set of network switches, which are programmable switches. And these end nodes can be Raspberry Pi or Arduino nodes, which can then be used to create an overlay network. The overlay network uses something called Ryu, which is a programmable network a library, an STM library, which can then allow us to dynamically create reservations on network switches, which are part of my end-to-end chain, right? So this is essentially where this, so being able to do this opens up the potential surface of utilizing AI. Okay, so essentially, if I look at what operating systems used to do in the past, so if I look at what an OS does in the past, an OS is essentially a process of thread management and coordination. An operating system often has a kernel architecture and does resource management, such as memory, I/O, resources, etc., managing within my system. It also supports things like user migration and state management within a computer system. An operating system, for example, can be extended through plugins or dynamic link libraries and so on. And operating systems will also give me security at various levels. So I can have SSL or access control libraries that help me to extend the capability of my operating system. So what an operating system does is it essentially provides an abstraction using the concept of processes or threads to manage my underlying resources. So essentially, an operating system is all the software you did not write, but something that your application needs to trust in order for it to work correctly. So if I look at an old version of an operating system, such as Windows, so Windows will have users at the top, and then they will have a collection of user services, and then kernel services, right? So things like I/O management and object manager and so on, and a hardware abstraction layer that essentially abstracts the hardware from the user, right? So we have a user application interface. We have support for coordination or management of services. We have abstraction support. We have a user versus kernel mode. And we have some support for extending the capability of what is present within the kernel mode. So the question I have for you really as researchers working in this space is, if AI were to replace some of these things in the kind of environment that I showed here, what would that AI look like, right? To what extent can we write AI services that help us to automate some of these processes, right? So that's the first question. And to what extent can we do it in an automated way? So if you look at the availability of hardware today, this is an example of edge computing and deep learning. So Intel has this thing called the neural compute stick. It's a deep neural network inference engine that is built on a USB stick. So here's a USB stick. It's a prototype that allows you to do what we call vision processing unit-based embedded devices. And inside the stick, you can have an architecture that looks like this. So there's a neural compute engine, which can do deep neural networks, an accelerator, an image pixel processing engine, for example. It has a number of onboard system support services, right? And it also has a number of what we call shave processor cores. So there are 16 very large instruction word or DSP type cores that sit within this stick, and there is a memory interface that allows me to connect to the underlying bus using a USB interface to my system. So here's an example of a very simple device that can essentially add AI to the edge of a network. So you can combine these sticks together using something like a USB hub, for example. So here I have 16x4 shaved cores which are working together at the edge of the network. I can integrate the neural stick within something like a Raspberry Pi. So this is a Raspberry Pi device where essentially what I'm doing is I'm enhancing the capability of the Pi with a neural stick that does the neural network, the machine learning, but integrated with a Raspberry Pi node. And I can also plug one of these neural sticks into a drone, for example. So if I have images coming off a drone, what the neural stick does is it can do deep learning, but directly on images that are captured off the drone. Right? So essentially, this is an example of where AI can enhance the capability that we have at the edge of the network by including it in devices that are often part of of my edge devices. So Intel has, of course, this idea that they have this concept of integrating these VPUs or using this shape processor cores for speeding up neural net execution. So the key thing to remember about this is that the stick, the neural stick, does not do any learning, right? It doesn't do any neural network learning. The only thing it does is it takes a learned model and it does inferencing once the model has been learned, right? So that's the important thing to remember here. Of course, Intel is not the only vendor out there. NVIDIA also has a set of services, for example, as part of the CUDA-X AI platform to create a number of libraries to do machine learning at the edge. And Huawei, which is this Chinese vendor, Huawei has a whole ecosystem of trying to create specialist AI processors that can sit both at the edge of the network and also within the data center. So hardware and system vendors are increasingly embedding AI into their platforms, right? So this is the idea here is that the platforms that you buy from these vendors already has AI within it, right? So the question is that as a developer, as a software implementer, to what extent should I reuse this capability rather than try to create my own AI and essentially replicate what the vendor is already giving me? So here's an example from Huawei. This is the Huawei's AI portfolio, where essentially Huawei is supporting a number of software libraries. So for example, TensorFlow, PyTorch, and Paddle are frameworks for machine learning. And so what Huawei is doing is as part of their offering in terms of hardware offerings, they're providing specialist architectural support for running things like computer architecture for neural networks, which can then be integrated with a number of different types of devices, right? From consumer devices to public and private clouds to edge devices and industrial IoT. And so the Ascend architecture from Huawei is trying to build on this neural network architecture to enhance this capability that sits at the network edge. And so, so essentially, the question really is as to if we know that this is out there, to what extent should a developer make use of this? Okay, so I just wanted to build on this. So another very interesting kind of focus on machine learning at the edge is this thing called TinyML. TinyML is doing machine learning, but on edge devices. So what TinyML essentially is saying is that often when we use deep learning models like with TensorFlow or Keras, these deep learning models assume the existence of a very large scale system to be able to do the training, right? So what TensorML is trying to do is to take a learned model that you have already trained in a data center and then understand how this learned model could be reduced in size and pushed towards an edge device, right? So they have this thing called MobileNet, which is essentially a two-layered network, which allows you to reduce the number of weights and other hyperparameters that can then be pushed into an edge device. And SSD Lite is a single-shot detector. It's a single-shot detector that can be used for detecting objects within images, for example, that can be combined with MobileNet and migrated to things like an Arduino board that can sit at the edge of the network. So TensorFlow Lite is an equivalent example of TensorFlow, but for edge devices. So it's essentially running machine learning on devices which have limited bandwidth, where latency constraints are a problem, and where security is a problem, where a user is not interested in connecting to a data center, but they would really like to do processing towards the edge of the network. And so this is really for devices which have very limited capabilities. So a flash memory and where static RAM is of this order in order to run these machine learning models. So the idea is that you train the network on a cloud environment, and using something called distillation and quantization of the learned model, where you take, for example, a 32-bit weight. So if your weights are captured using 32-bit numbers, you try to distill this down to, for example, 8-bit numbers, which can then be pushed towards the network edge. And so essentially, it's the ability to trade off accuracy with performance. And so just to give you an example, so if you take AlexNet, which is a convolution neural network, typically used for image processing. So typically, an AlexNet algorithm will have typically about 50 million weight parameters, right? So if I use 4 bytes, which is 32 bits, to encode each of these parameters, I get essentially a weights file that is 200 megabytes in size. So this is just the weights file, right? This is not any other parameters associated with the network. So what TensorFlow Lite is saying is that, can I compress this weights file and shrink it to less than 4 bytes, right? So, and the TPU, which is a tensor processing unit version 1 that was shipped by Google, was essentially using this concept of 8-bit quantization as a way to shrink the size of the weights file so that it could be pushed towards edge devices. So there's more details here if you want to read up a little bit more on this. So just to give you more details on TensorFlow Lite, and just one other thing associated with it is, like TinyML and PerfML, which is machine learning performance library, PerfML has another subgroup working within it called MLPerfTiny. So this is really about trying to utilize machine learning on these type of processors. So it's AMD Cortex-A7, which is used in a variety of chips around the world today, because it's like one of those cores that are integrated into other processors. The STMicro's 32-bit microcontrollers, Raspberry Pi, and Arduino Uno, these are all microcontroller-based systems. So we have a number of benchmarks that you can use to train or validate your deep neural network, convolution neural networks, recurrent neural networks, or LSTM, the long short-term memory, on these kinds of edge devices, right? So this is a good kind of benchmarking exercise. And just to give you some more details on TensorFlow Lite. So TensorFlow Lite is like an interpreter that you can have on an edge device, which can essentially do inferencing on the data, and it supports a set of core operators that are adapted for these edge devices. So essentially, it tries to map a execution workflow as a static graph, which can then take up less memory that you can then use on an edge device. And it uses a converter that takes a TensorFlow model that has been trained on a cloud platform and pushes it into a TensorFlow Lite model using this concept of quantization that I mentioned before. So it takes a TensorFlow model and then does model optimization on it, including quantization that can reduce the size and increase performance of models without losing accuracy to some extent. It also uses this technique called flat buffer, which is a way to essentially do serialized access to data and minimize the amount of I/O overhead required for handling data that is then shipped into these machine learning models. It can be run both with Android and iOS systems using Swift, for example, for iOS, including running on microcontrollers such as Arduino. And where GPUs are available, so right, all edge devices are not the same. Some edge devices will have GPUs. So if GPUs are available, it then maps these quantized weights into floats that can then be run on GPUs. So quantization will basically remove floating point and convert it into a set of integer weights. And so therefore, assuming that your device does not have access to floating point units. So essentially, it can do this kind of optimization based on the type of devices you run these on. And the other really important part of TensorFlow Lite is that it has a number of pre-learned models. So models for image processing, for object detection, for pose estimation, etc. So it has a library of models which you can then use out of the box to then try to parameterize them in some way. So it's a very interesting use of machine learning, but for edge devices, for devices that sit at the edge of the network. So if we see, for example, on the other side of the spectrum, the compute power used in large-scale AI continues to grow. So this comes from this website over here, where compute used in the largest AI training run has grown over 300,000 times over the last couple of years, right? So from AlphaGo to the use of AlexNet, which I just mentioned earlier. So there's a constant increase in the amount of compute power we need. So essentially, we have two perspectives then on machine learning. One is machine learning on edge devices very close to the user, and the other is the use of machine learning on large-scale systems like HPC resources. And really, my argument is that we need to connect these two together in order to really benefit from AI, not just in the data center, but also the AI at the edge. And combining those two layers is really the really interesting challenge going forward. Okay, so the other question in AI is understanding what the AI algorithm is actually doing. So an explainable AI. So again, many vendors seem to have focused so much on trying to improve the performance of AI, but not really trying to tell us what the AI is actually doing under the hood. So balancing interpretability with accuracy remains an important challenge, right? So the question here is that I might be able to get a very accurate model from a machine learning algorithm, but I may not be able to fully explain what it's doing. So this explainable AI debate, especially with the use of machine learning and neural network models, has been trying to create approximations of what the AI algorithm is actually doing. So use of approximations is a key mechanism to tell us what the AI. This may not always be possible, of course. So the way we do this is we try to find the focus of a deep learning network. And this is very easy to do when you do image processing, or one of the most kind of widely used techniques within machine learning. So if I have, for example, an image that looks like this, what I can do is I can try to understand where the AI algorithm is actually focusing on, right? So these heat maps that you can see here will tell me where the focus of the AI algorithm is. So if I'm, for example, trying to identify a dog within this picture, and if I give it a number of training examples of this object, what I'm trying to really understand is that where is the AI algorithm focusing on as part of the image? So GradCam is creating a visual explanation for decisions that have been made by the AI algorithm by identifying or highlighting pixels of interest within an image like this. So once again, we are trading off. GradCam will essentially can only be applied really to image processing. However, trying to identify how GradCam can be perhaps migrated to machine learning for systems remains a challenge. Okay, so here's another example. This is feature visualization. So what this does is it takes a neural network, for example, and it tries to plot the images, so what each neuron is doing at different layers of my deep learning model. So if I move through the deep learning model as different layers of the neural network, I can essentially plot out or visualize what each neuron observes as part of this data set. So data set examples will show us what neurons respond to in terms of training inputs as their stimulation as part of their activation functions for each of the input vectors that are put into them. So optimization will isolate the cause of the behaviors from mere correlation. So a neuron will be able to detect, for example, what you initially thought the neuron was responding to may not always be the case. So here we can use feature visualization to generate images which lead to activation of certain neurons and identify or isolate effects of individual neurons to tell us what is happening within the network. So another technique, which is called contrastive explanation model from IBM, is essentially creating instances. It uses this concept of instance-based local black box explanations using these two techniques called pertinent positive and pertinent negative. So pertinent positive says that in order for me to explain what this model is doing, these are the minimal set of features that should be present within my data set. So features that should be minimally and sufficiently present to predict the same class on the original instance. And similarly, pertinent negative is a negative of that. So what should be missing from it, from this explanation? So by combining pertinent positives and pertinent negatives, I can essentially create a kind of explanation of what my AI algorithm is attempting to do. And finally, the other one, which is very popular right now, is LIME, which is a local interpretable model agnostic explanation. So what this is saying is that even the most complex models can be approximated using some kind of simpler linear model, a locally linear model. So what LIME does is it generates an explanation by approximating the underlying model by some interpretable model, such as a linear model that underpins the use of this neural network. So here, for example, if I have an image, it will try to create different explanations of what the neural network is doing. And then depending on what each of these different models tell us in terms of what probability of object that it observes leads into the outcome, it then combines these together and says, this is the most important feature, right, that I observe within the image that leads to this output being classified in the way it is, right? So it essentially takes the original model, the original image, and then tries to identify portions of the image that lead to the output that I'm observing and uses the most observed part of that image, the local linear model, to explain what the output is actually telling me. So these are examples of explanations that you can generate from these underlying machine learning models. So the other important part is that when I'm utilizing this concept of machine learning, I need to feed these parameters. I need to identify the parameters on which I'm actually training my machine learning model. So if I take elasticity, which is a very, very important part of using systems and AI together. So it's the degree to which a system is able to adapt to workload changes by provisioning and deprovisioning resources within a computer system, such that at each point, the available resources match the current demand as closely as possible. So the question is that if elasticity is a parameter that my AI is trying to optimize on, what are the kind of metrics that the AI can learn on? So I'll give you an example of this. So for example, when we look at speed up or scaling up speed, we switch from an under-provisioned state to some optimal or over-provisioned state within a cloud environment. So we can consider, for example, the temporal aspects of how we scale up given our current state to the number of resources that we want our system to have. And the deviation from some actual to required resource demand is essentially what the AI uses to say, this is my current state, this is the state I want to be in terms of some optimal use of my resources. So how do I get there? How do I use learning as a way to go from my current state to some known optimal state or expected optimal state? So the role of predictive allocation for known events is often been used in terms of virtual machine or container allocation within some cloud environment. So elasticities can be defined in this way. So if I take this example, so here on the y-axis, I have number of requests per second that are coming into my computer system. So this could be number of tasks or number of jobs that are being submitted to my system. And I have a workload that looks like this, right? So I have the workload suddenly increases at this point in time. And then suddenly I have a gradual decrease in the workload. So we can think of it like this, that I have a service level agreement where I want a response time to be less than 2 seconds, 95% of the time. And the resource demand to say is, what is the minimal number of virtual machines which are required to match this SLA requirement? Okay, so what I can do is I can take a workload intensity like this, and I can match it to the number of virtual machines I currently have within my system. So what I do is I start with 3 VMs, then I suddenly increase the number of VMs as I see an increase in workload, right? Then I sustain the VMs to 8 VMs. And as my workload decreases, I reduce the number of VM instances that I need. So what we can say is that at some point in this kind of allocation of resources, the light curve here is the over provisioning of resource. So I'm actually need 2 VMs, but I'm actually running over in an over provisioned state. then I have an under-provisioned state, and then I have an over-provisioned state, right? So essentially, if I track my workload in time and resource allocation in time, I have a behavior of a system that looks like this. So the question is, right, if my intention is to identify the optimal or the minimal number of VMs, right, how can I learn this profile, right, in order to meet this SLA? So that's what the AI will now try to do. So we can think of these two systems. So system A and system B are two different type of AI systems that try to match the same workload. And if I look at this, they have two different over-provisioned and under-provisioned profiles. So this has under-provisioning here and over-provisioning here. This is over-provisioning here and under-provisioning here. So now I have two potential machine learning systems which are trying to match this workload profile, but in two different ways. So which one is better, right? So that's a question that we can ask on the AI system. So what we can do is we can take the workload and we can divide the workload into, we can divide the workload into periods of under provisioning and over provisioning. So A1 is where the system is under provisioned, and O2 is where this O is where the system is over provisioned. So over a time period T, right, we can identify the periods of under provisioning and over provisioning and estimate the benefit that a certain AI algorithm is doing based on this kind of workload. So we can create metrics like these. So we have the average switch time from an under provision to an optimal or over provisioned state. We can have the accumulated time in some under provisioned state, and the average amount of under provisioned resources during an under provisioned period. Right. So what we can do is we can come up with these metrics which says over this time window T, how much under provisioning takes place, and over this time period T, how much over provisioning takes place. So by comparing PU and PD, we can take two different AI systems and estimate the benefit that they're doing for scaling purposes. Right. Similarly, we can also look at therefore elasticity measure. Elasticity 1 is 1 over the average state transition from under provision to over provision versus over provisioned to the optimal state. And we can again compare how elastic a given resource allocation strategy is if it uses a machine learning algorithm. So really what this is trying to say in summary is that what are these parameters? What are these monitoring parameters which help us understand the over and under provisioning state? And how can we expose these to an AI algorithm so that it can do this kind of allocation that we see here with variable workloads within my system? So essentially the question here is to how can applications make use of AI, and what are the parameters, right, that we need to expose to the AI algorithm so that it can act essentially as this kind of controller? What is the location or influence of this data controller? So that means that to what extent does AI have control of changing the parameters of my underlying computer system? And what degree of control does the system actually have? And how do we separate the control logic, right, or behavior from the underlying data path that sits within my system? Right. So what are the parameters that I can expose to the AI algorithm? How do I know what the AI algorithm is doing? And how can I separate the influence of the AI algorithm from the underlying data that is present within my system? So based on these, we came up with these two architectures, which I just wanted to also have discussion on. So the application essentially talks to a resource manager, and the resource manager has a number of resources that is trying to control as a kind of a scheduler or essentially some kind of resource environment that manages the containers or VMs within the system. So what this is saying is that normally we have a forward scheduler which takes an application, it uses a resource manager, and it manages a bunch of hardware infrastructure here. What we're saying here is that there also should be something like a reverse scheduler. What the reverse scheduler does is it takes the properties of the resources and then tunes the application to make use of these resources here. So essentially it says the application should be dynamically tuned based on what resources I have available. So you can think of it like this, that if I have a image processing, if I'm trying to take an image and trying to process on these resources, so I don't partition the image based on the number of resources I have, but the number of resources and the capability of these resources should help me tune the application itself. So we call this concept of tuning or tuning of the application based on the properties of the resources I have. So if I knew I had edge resources available in my system, how can I dynamically change the workflow graph of the application to match the capability of the resources? So that's where AI can be used in one way. The other approach here is where we do autonomic tuning by the application itself. So the application does is the application dynamically uses an autonomic tuner to train or change the properties of the resources. And what it does is it essentially learns what resources it has and then influences the resource manager, very much like the elasticity example that I showed you. So the application works with the resource manager and then tunes the properties of the resource pool based on what it observes or monitors of how this resource manager uses this resource pool. So we can use resource reservation to achieve a particular quality of service criteria, and we can dynamically assess data streams, for example, to modify how the resource manager uses these resources based on some tuning engine, right, that links with the application itself. So both of these are examples of using AI along with the resource manager that essentially works with a resource pool within my system. So essentially the idea here is how can we combine a set of task execution nodes with a bunch of learning nodes within my system. So this paper describes this in a little bit. This paper describes these architectures in a little bit more detail, where what I do is I run some execution tasks, some application tasks within my pool of resources, within my collection of resources, but then I combine them with nodes which are trying to see how the underlying infrastructure is doing. So these are learning nodes. So I partition my resource pool into execution nodes and learning nodes. The learning nodes are observing the execution nodes, and the learning nodes are dynamically adapting the resource pool, right, based on how they utilize these underlying resources. So we use this concept of tuning or learner nodes alongside the executor nodes. So this is the idea. So essentially we try to use the data center, we try to use our pool of resources. For example, here we use something called Energy Plus. Energy Plus is a simulation environment. But what we do is we take Energy Plus and we combine it with the neural network training that runs alongside Energy Plus as a function approximator of Energy Plus. So we take Energy Plus as something that is running on an HPC resource. We combine it with a set of nodes which are observing the use of Energy Plus, and both of them working together can help us to dynamically tune the use of Energy Plus itself. So Energy Plus usually takes minutes to run, for example, but the neural network training, often the neural network training itself takes minutes to run. But once we've trained the model and the model is running alongside Energy Plus, the execution of the trained model often takes seconds within my data center. So it essentially is trying to combine a model execution alongside a machine learning model that can then tune this execution in some way. So, and essentially when my mean squared error starts going beyond a certain value, then essentially I try to retrain the neural network model itself. So each Energy Plus execution provides potential training data that can then be used by the neural network model. So this paper, you can see it in more detail. So here what we're doing is we're trying to combine Energy Plus execution, which is shown in these black lines, with the use of a neural network training. So essentially what this says is that I'm essentially, by combining neural networks and the use of Energy Plus, I can increase the completion ratio of how many jobs I can run within a certain type on a set of resources. So this uses both edge resources and data center resources together, combining the use of Energy Plus and the use of neural network training. Okay, so that's an example of how we try to combine these two types of resources together. Okay, so the last part of my talk, which I'll just mention for about 5 minutes or so, is a few years ago, we ran an application survey where we tried to identify a class of applications which we call high workload or high data workload applications. So here the idea is that these applications generate data in real time. So essentially these are called D3 applications. They're dynamic data-driven computational science applications. So they generate data in real time on demand, and they're adaptive in the sense that their processing or storage granularity can change over time. So the other important thing is that in these applications, we do not know how much data is going to be generated, right? So the computational resources have to dynamically respond in real time to the data workloads, right? So these are often stream processing applications where we do not know how much data is dynamically generated, and therefore we cannot pre-reserve resources to run these applications. So essentially we are trading off, for example, frequency of access with the type of analysis that we do on these type of applications. In-memory processing is often a very important part of these applications, and they have a high disk or I/O overhead in these type of applications. So we considered a variety of applications that had these kind of characteristics, where they're real time, they have on-demand data generation with prediction of resource properties, very hard to do in these type of applications. So what we did is we interviewed a number of computational scientists. We did a survey of these types of applications. So you can find this in this paper, introducing distributed dynamic data-driven or data-intensive science. And the applications that we cataloged, right, are divided into these categories. So we have Montage, which is essentially an astrophysics application. Nectar, which is for blood flow within the human body. So it models blood flow within the human body. Couple fusion, asynchronous replica exchange, climateprediction.net, and Scoop, which is essentially an ocean observatory application. And what we did is we took each of these scientific applications and we divided it into these 4 vectors. The 4 vectors are: what kind of execution units does it have? Does it have sequential or parallel DAGs, essentially directed acyclic graphs? Does it use files or messages or pub/sub, which is publish, subscribe, as a way to do communication? What kind of coordination mechanism exists? Is it master-slave? Is it data flow oriented? Is it SPMD, right? Single process, multiple data. And what kind of execution environment does it have? Does it have MPI? Does it use data streaming? So essentially what we are saying is that if we take a computational science application and we partition it into these 4 vectors, then we can apply machine learning to each of these vectors, right? So now I can use machine learning to manage my DAG, or I can use machine learning to do coordination of the data flow, or I can use machine learning to do co-scheduling. So machine learning and AI can now be applied to each of these vectors. So if I'm trying to write a new computational science application, if I were to divide it into these 4 vectors, then I can apply AI to each of these. So it's a kind of opening up the parameter space to which AI can be applied within these kinds of applications. So essentially, we were interested in what are the application vectors, what are the pieces of distribution that we can use in these kinds of applications, right? And provide a theoretical framework to analyze computational science applications based on these vectors. What are these axes, right, that we can use, which are common across different types of applications? So again, as I mentioned, so they use different types of execution environments, from MPI to they use special type of portals, to Juxta, to BOINC, for example. So these are different type of systems. And so the other question we had is that what are the common software libraries or software systems that these applications use? And so how could we learn from one application to another in how we apply AI or machine learning to these? So essentially the idea is that there's a large number of potentially unstable programming systems, tools, and deployment environments. So what we wanted to understand is that how do these applications make use of this? What are the common themes across these applications? And can we swap in or swap out these different vectors? And can we use, analogous to development of operating system services, can we identify common services? And can we utilize machine learning mechanisms to apply to each of these services? So that really was the context of this work. I'll just finish off here. So essentially what this talk is, what I was trying to identify in this talk was based on these three questions: that can we utilize abstractions and design patterns that enable us to utilize AI-based techniques more actively within our systems? So can we use programmable infrastructure that is currently available through this edge network and data centers? Can we use programmable infrastructure to use AI strategies within these multiple layers? So as we open up our underlying systems to use of elasticity, for example, what parameters are available to us which can be tuned by this AI environment? And how can we use the outcomes of these on the resulting application? And how can AI, which is available in hardware, help us accelerate, right, the use of these AI algorithms on these underlying resources once we have identified what these tunable parameters are within my system? So essentially that's a talk, and I'm happy to take questions.
Dr. Rana, thank you very much for your wonderful presentation, and it is very interesting subject actually, and you have been doing this research I think quite like a couple of years, but there's a background like a HPC and cloud computing and edge computing also. And we have some questions. I have also some questions, but let me read the question from the chat. From Fadishar: what is the feasibility of employ AI machine learning computation on the edge as opposed to on cloud?
Okay, so essentially many of the focus that has been there so far on machine learning has been on using large-scale systems to make use of AI. So these are, if I look at many machine learning libraries like Caffeine or TensorFlow or Keras, they're really meant for high-end resources. So you really need a large number of resources to train these models. So TinyML, if you look at TinyML, the idea of TinyML is that once you have trained the model, because often the neural network training takes a very long time. But once the model has been trained, right, it's just a set of multiply accumulate operations that you need to apply when you do inferencing. So when I apply a tensor, for example, to a convolution neural network, I'm really doing multiply adds. And these kinds of libraries that are like TensorFlow Lite is really meant for deploying these learned models on edge resources. What is really interesting going forward, right, is to what extent can we actually learn at the edge? Now, that is really an interesting area that is beginning to open up, because it's understanding that when you combine not just the inferencing model of a neural network, but if you start learning at the edge, can you do learning with a weight range, for example, that at 8 bits? So rather than use a very large range of weights in your machine learning model, can I reduce the range of weights and therefore the range of parameter space that I need to consider? And what is a trade-off in accuracy and performance that I can do when I actually do training at the edge? So that's really a very hot area right now in this space.
Okay, thank you. There is another question. Thank you. It was excellent work from Beytullah Yıldız. How is it possible to combine optimally HPC and edge at both ends?
Okay, so that's a good question. I don't think I know the answer to that. I think that's a research challenge that we are trying to understand, exactly as you said. So the question for me really is, how do I partition a machine learning algorithm between the edge, the network, and the data center? Because the network itself can offer me programmable slices to the use of SDN and network function virtualization, where some of the functions within my network can also do some initial pre-processing on the data. So for example, if I take a neural network, like a deep neural network, if I look at the early layers of the neural network, which are processing the input, I'm doing some very simple things in that network, right? I may be pre-processing data, I might be partitioning or filtering out data. So can I partition a deep neural network across these different layers of the network platform. So some of the layers can run at the edge, some can run within the network, and the more complex layers can run within the data center. And we also have other published work where we try to partition something like a DNN across these different layers of this infrastructure. And I'm happy to share more of that with you.
Thank you, Doctor. Another question from Mehmet. Great talk. Thanks for being with us today and giving this talk. I am interested in your recent review conducted on data-intensive applications. Have you looked at the requirements related to the use of machine learning, deep learning on the data lineage or data provenance metadata generated by the data-intensive applications?
So let me just see requirements related to the use of machine learning on the data lineage or data provenance metadata. Okay, so data provenance or essentially understanding the data trail is an interesting area. So we have not looked at that. I think that would be a very interesting model to understand how the machine learning model evolves over time based on the kind of data footprint that it generates. So I'd be very interesting to talk to Mehmet more. So please drop me an email. So this whole talk was really meant to be a dialogue, right? There are a lot of open issues we are just touching the surface of. So I'd be really interested to learn more from Mehmet on this.
Yeah, I think he's Mehmet Aktaş. Also, he worked with Jeffrey Fox, and his PhD students actually working at Yıldız Teknik University. He will contact with you probably. And there is another one I missed actually. Thank you for inspiring presentation from Hasan Bulut. Is explainable AI an outcome of an effort to trust AI? Is it also possible to model every computation with AI techniques? And what can we say about the accuracy of a computation modeled by AI compared to traditional computations?
Yeah, so that's a good question. So I think in terms of explainable AI, so the idea of, so the question is, right, there's a whole community right now working in this area of explainable AI. It's essentially is trying to understand what the AI model is doing. The question is that with the machine learning model, because of the number of parameters that we have available within a machine learning model, many of the scenarios that I've seen are really trying to balance accuracy of the model itself with with what you have observed within the model. So it's really trying to approximate or trying to simplify the behavior of the model in some way. So explainable AI is of course is a huge kind of growth area right now. So essentially the work that I've seen is really trying to create a very limited accuracy representation of what the machine learning model is doing. So I think that's what I have seen so far. But the problem with many of the vendors today is, everybody's so interested in performance, but doesn't tell us what the model is actually doing. So what is available within the box. So if I look at the other part of AI, which is the more logic-based models or logic-based representation, where we could encode the properties of an AI algorithm using a set of rules, for example, we could express the behavior of the AI as a bunch of rules which we could then reason over. Machine learning has kind of moved away from that space. So if we could somehow take a machine learning model and try to express it as a collection of rules or some simple rules which we could then analyze and reason over. So that would be a very interesting explanation that we could derive from that AI model. So again, there's a whole community of researchers looking at that space also. Yeah, so.
Thank you, Doctor. There's another question from Galip Aydın. Thank you for an excellent talk. And what do you think about the future of Intel OpenVINO as opposed to NVIDIA Jetson family? Which one seems to be gaining wider adaptation or will gain in the near future?
Yeah, so I think, I'm really, very interested in NVIDIA because NVIDIA has just bought ARM. And, whereas NVIDIA was very much kind of focused on, the high-end data center type resources. But when you put NVIDIA and ARM together, you really have the end-to-end AI. Because ARM Cortex, for example, the ARM core is part of so many devices that we use today. And combining the ARM together with many of the NVIDIA resources would have a very interesting future, for instance, in this kind of layered structure that I showed you from the edge right up to the data center. OpenVINO, on the other hand, from Intel, is primarily intended to be a development environment, a development environment where you can essentially have portability from things like Intel's VPUs and tensor processing units that are being proposed, right up to the use of the neural net stick that I mentioned. So OpenVINO is really about portability of learned models for inferencing versus learning, whereas I think NVIDIA has a much wider collection of hardware infrastructure, especially with integration of ARM. So we are really keen on NVIDIA and see where that goes.
Okay, thank you. I have one question, Doctor. On the edge computing, if you use the machine learning AI and you train the model, then you put on the edge devices like the Raspberry Pi or Arduino. Sometimes, there might be some difficulties, or there are some standards. There are not so much common standards for using machine learning on edge devices. Is there any future? I know there are too many research in this area to have some using effective devices using the machine learning on edge devices. Is there any limitation or advantages, or what do you see from your point of view, from your research point of view, for limitation or advantage of edge devices using machine learning?
Okay, so we see a number of advantages. So let me give you an example. I didn't have enough time to explain more examples of applications. So for example, suppose you have an edge device and you have a data center. The current model is that you take all the IoT or edge data and you push it into a data center where the model is built. The problem occurs is what happens if the network breaks between the edge device and the data center. So now your edge is out of sync with your data center. So if you have a learned model that sits on a data center that controls the edge,
Yes.
So what you really want to do is that network connectivity could be just because the network is slow, or you might have a cyber attack on the network itself. So what you really want to do is to take that learned model and push it towards a network edge and primarily do inferencing at the edge. In terms of portability that you mentioned, portability can be provided through container frameworks. So what you could do is if I had a container framework, which is a very low overhead container. So within Docker, for example, we have a very small container framework called runc. Runc is a very low overhead, low memory footprint container framework that we can run on even edge devices. So we've done some benchmarks of using runc directly on Raspberry Pi, from Raspberry Pi 0 right up to Raspberry Pi 4. And we've looked at the kind of performance overheads of doing analysis on these different type of container frameworks. So portability or interoperability, as you said, can be achieved through the use of common container frameworks, which could then be hosted on these edge devices. So it doesn't matter what the hardware is, as long as it supports that type of container framework. So I think having learning at the edge supports security, it supports latency, it also supports this interconnectivity between the data center and the edge. So the edge opens up a lot of very interesting application areas, which are not possible purely on the data center.
All right. And good. Sorry, Doctor, we have some other questions.
No,
I have also, but we are out of time. Actually, the sessions are starting, and it was a wonderful talk. Actually, I hope can we get the slides, or can we share the slides with us? Then we can, if it is possible. And thank you also for available time. Then thank you for our guests for joining the session. We have actually also YouTube channel. Benov also joined the YouTube channel. Thank you very much, Dr. Rana, for your wonderful talk again. And if you don't have anything else, I would like to end the session. Yes.
Thank you. Thank you very much. Thank you. Take care. Okay. Have a good day. Thank you.
Too.
Bye-bye.
Thank you very much. And thank you again. Bye.
Thank you. Bye-bye.